We're going to look at using Prim's algorithm to find the minimum spanning tree for the undirected graph in example C.10.6 in the text. We have the graph here at the top and its matrix representation below. Each one of these edges in the graph corresponds to two entries in the matrix. Because the graph is undirected, we have A to B, this edge here, recorded here and here. As we proceed through this solution, we would like you to look at both the graph itself and the matrix. Prim's algorithm decides to start at a particular vertex. So we're going to choose to start at vertex A, and two things happen. One of them is on the graph, you record the fact that you're at vertex A. I'm going to make these red. And on the matrix, we are going to mark column A as having been visited by marking it as red as well. The second thing that you have to do at every stage in the algorithm is identify the edges emerging from your current vertex. On the matrix representation, this is done by marking up the column that relates to that particular vertex. Since we will not need to come the other way, we can actually blank out as not usable anymore the row for A. So all these things need to happen. You choose your vertex and then you blank out the column. You mark the column as green, we're about to choose from that, and the row corresponding to this vertex can now be removed from the discussion. Prim's algorithm asks, it's a greedy algorithm, so it asks you to select the cheapest edge. And the cheapest edge is the one that goes to B. So at the next step, we are going to move on the graph itself to vertex B, and on the matrix, we are going to move to column B. Notice also that simultaneously we do not need the edges that go in the opposite direction, so we can remove row B from the discussion at the same time. Being greedy, we pick the cheapest green edge of all of the edges that are currently green. And this is 1. On the graph itself, that's this one. So on the graph, I hope you can see that we will now proceed to vertex E. And on the matrix, I hope you can see that we are now going to go to column E, because it is E that is the next vertex of interest. So the next stage is on the graph itself to include vertex E and to mark the edge BE as being part of the spanning tree. And on the matrix, we are greening up the column E and removing the row E. And again, we will now look for the cheapest edge that's emerging from any of these. So we're looking at all of these numbers in green and picking the cheapest one. On the matrix, that is this entry, and on the graph, it is this edge. So both indicate that the next maneuver will be to go to vertex F. So we will do that. At every stage, notice on the graph, we are trying to avoid making cycles. So I'm making green edges, the ones that we wish to avoid, and on the matrix, these are the ones that are greyed out. So we're now at a vertex F. On the graph, we're here, and in the matrix, we're in this column. And you will see that I have greyed out row F as well. Being greedy again, we are looking for the cheapest edge that emerges from our current tree. Now, this means looking at all of them. We could have picked that one, but I've chosen to pick that one. And this is the equivalent of moving on to vertex D. So that's here now. So we're going to next move to vertex D, and that is from B to D. notice, we have readied the edge from B to D, and that's been added to the tree. So the tree, we're growing the tree on the graph, but simultaneously we have greened up column B and removed row B from the discussion as well. Being greedy again, we're once again looking for the cheapest edge that emerges from any of the current tree. So we're looking at all of these green numbers here, and the smallest one is in row G. On the graph, the cheapest edge out of the tree at the moment is the one that goes to G. So our next step is on the graph to red out the edge that goes to G, and on the matrix we are greening up column G and blanking out row G. There's obviously only one thing left to do now. We've only got one column and one row that we haven't visited, and on the graph we have only got one vertex that we haven't visited. So we're on the last lap now, and we obviously pick the cheapest way of getting to this remaining vertex, and it is this edge DC. On the matrix it's here. The matrix is completely used now, and notice that we have visited every vertex on the graph. So we have successfully used Prim's algorithm now both on a graph and on a matrix to solve this spanning tree problem.